Welcome. So we were discussing the operations that will be performed on the independent variable. We already discussed one operation, that is the time scaling. We also tried to understand the physical significance of time scaling. Fine. And we concluded that for continuous time case, if the scaling factor is greater than 1, it will lead to the compression of the signal. And for the discrete time case, if the scaling factor is greater than 1, we will be losing some samples that were originally in the input signal. Yeah, that were in the original signal. Now the second important what you call operation that is performed on the time that's performed at the independent variable is what we call time reflection. Fine. And again, we'll go for the mathematical definition first. Then we'll see what actually physically happens to the signal. Now again, mathematically, it's quite simple. You have an original signal x of t. This will be my original signal. Then I am defining a new signal y of t, which will be the time reflected signal. And mathematically, it is simply you negate the time. That is, t is replaced by minus t. Fine. And this signal y of t, it basically represents a reflected version of x of t. Fine. Okay, so graphically it will be a simple thing. If I have a simple waveform, this is my time axis, this is my amplitude axis. Suppose I have a waveform which is defined for positive, something like this. Then when we perform time reflection, the change that you will observe is that your waveform will be reflected. So this will be time, this will be y of t, which is x of minus t, so it will be on this side, something like this. Fine. So we say that it is the reflected version, and the reflection has been made about this amplitude axis. Fine. First it was the right side of the amplitude axis, then when a time reflected it, it went to the left side of the amplitude axis. Fine. Now in our classification, if you remember, we did a classification based on the symmetry, classified signals as even signal and odd signal. So you know that for even signals, they follow a property that x of t is equivalent to x of minus t, and for odd signals, x of minus t is equivalent to minus x times t, which means if you perform time reflection, if time reflection is performed on an even signal, there will be no change. Fine. Because once you perform time reflection, you are basically doing this operation y of t is equal to x of minus t. But for an even signal, x of minus t is equal to x of t, so it is like this. Okay? So even signals, they are the same as their reflected versions. Odd signal, there will be a difference. So I can kind of generalize that even signals, they are the same as their reflected versions, right? But odd signals are the negative of their reflected versions. because for an odd signal x of minus t is minus x of t. So while this was for even, for the odd case it will be like this. Fine. Then similarly you can project the same thing in the discrete time case. So we can write y of n is equal to x of minus n, and that argument odd and even, it also applies for the discrete time case. So this is yet another operation that we perform on the independent variable, that is the time variable. So we have time scaling, then we have time reflection, then we have the third one, again a very important operation as far as signals is concerned. This is called as time shifting. Fine. And mathematically it is defined as that you have an original signal y x of t, and we get a time shifted signal by applying some shift to the time. So here t naught, it is the time shift. Fine. Now again it depends upon the value of t naught, whether it is positive or negative. So we have two generalizations here, that if this time shift is greater than 0, that means a positive value, then the signal x of t is shifted intact to the right. Fine. To the right of the time axis, relative to the time axis. And if t naught is negative, that it has a value less than 0, then the waveform, yeah, you can say the signal itself, the signal x of t is shifted again intact. There will be no loss, there will be no compression, expansion, or loss of samples in the discrete time case. Intact is meant here in that sense that your signal, it will not lose anything, it will only be shifted. So the signal x of t, it will be shifted intact to the left. Fine. And the same argument follows for the discrete time case, that y of n, it will be x of n minus n naught. Here again n naught is a time shift, and if it is greater than 0, signal will be shifted intact to the right. If it is less than 0, it will be shifted intact to the left shift. So we can either have right shift or the left shift. So let's do a quick example. We will take the discrete time version because it is more perceptive, we can perceive it in a much better way. So let's suppose I have an original signal. We will do the graphical analysis. We have an original signal. We'll take a small signal here. We'll take only few samples. Okay, so this is my original signal, say x of n, and let's define n naught having some positive value. Fine. So let's suppose for the first case n naught has a value of say 2. Now let me arbitrarily define my original signal. Suppose it is having sample values 0, it's having this value, then suppose this is 1, then suppose it is 2, then 3, then 4. Right, let me just mention the values here. This is the value at times 0, 1, 2, 3, 4. Right, So I have in total 5 samples. Now I have to derive the time shifted version of this signal. So here n naught has a value of 2. So what I'm actually trying to plot is this. This will be n. I'm trying to plot y of n, which is equivalent to x of n minus 2. Fine. So if you wish, you can do that tabular approach to get the individual discrete values. So this will be n, then this will be y of n, x of n minus 2. So if n has a value of 0, it is y of 0. We will have x of minus 2. For 1, it will be y of 1. Then it will be minus 1. For 2, y of 2, x of 2 minus 2 is 0. Similarly, you can construct the table y of 3, x of 3 minus 2 is 1. 4, y of 4, x of 4 minus 2 is 2. 5, y of 5, x of 5 minus 2 is 3. That is x of 3, huh? Then y of 6, it will be x of 6 minus 2, that is x of 4. So it means y0, y1, y2 is, y0, y1 is x minus 2, x minus 1. Now we don't have any value at minus 2 and minus 1. Fine. So just to make you understand, so that if this is minus 1, let me change the color of this. So okay, this point is minus 1, this is minus 2. There are no values, no sample values at minus 1 and minus 2 in the original signal, which means if you go by this table, n is equal to 0, n is equal to 1, that is y of 0, y of 1 will have values x minus 2, x minus 1. So they will essentially be 0. So 0, 1, 2, 3, 4, for your reference. Okay. So at 0 and 1, we don't have any values. So no value here, no value here. Then at y of 2, we have x of 0. Now x of 0 is defined. It has this much of value. So this value will appear here. Similarly, y of 3 will have a value of x of 1. So y of 3, that is this, will have a value of x of 1. Then again, y of 4 will have a value of x of 2, y of 5 will have x of 3, y of 6 will have x of 4. So if you just visually compare this waveform with this waveform, you can see that the signal is intact. You haven't lost any samples. The 5 samples, they do exist in this waveform also, just that they have been shifted towards right. Fine. Similarly, if you can, let me just quickly draw that. If you have the same signal, so defined at 0, then a sample at 1, sample at 2, sample at 3, sample at 4. And if I define, so this is my x of n. Now for this case, if I define n0 having a value of say minus 2, which means y of n, it will be x of n plus 2. And if you do the same calculation, this tabular form, you will observe that it will be shifted towards left. So essentially what it means is 0, 1, 2, 3, 4, minus 1, minus 2. So the entire waveform will be shifted towards left by 2 units. So 4 sample will appear at 2. 3 samples will appear at 1, the value at 3. The value at 2 will appear at 0. Value at 1 will appear at minus 1. So 2 appears here. So 2, just a second. So it is slightly lesser. So it is this value. Fine. Then here and finally here. Again, we haven't lost anything, no sample is being lost, just that the entire waveform is intact and is shifted towards the left. Okay? So if I have to generalize some properties about these three operations that we discussed, turns out when you do scaling, you are bound to lose some information. If you remember in our first lecture, we defined signal as something that carries information, that conveys message. Now in time scaling, you are doing compression, whether it is the continuous time case, yeah, you are losing samples, whether it is the discrete time, in the discrete time case, which means since you are losing something, you're losing a part of your waveform, you're compressing it. Yeah, in the discrete time case, you are losing some samples. So discrete time case, it is clear, you are losing some samples means you are losing some information. Continuous time case, you are compressing the signal. Fine, try to understand, although it will be slightly difficult at this point of time, but I want to you people that you should have some physical insight what actually is happening. Mathematically it's fine, you can do substitutions and plot those values, you'll get the output, but what matters is the physical implication. Now time scaling, if it is the discrete time case, you are losing samples. Fine. And if it is a continuous time case, there may be compression or expansion, which means your waveform is being altered, the content it contains, the information it contains. Either the information is compressed or some samples are being lost. Now the challenge is that if you are doing time scaling, for example, if we consider the discrete time case, because it will be easy to understand, the challenge is you are performing scaling. Fine, your samples are lost due to scaling operation. Now the challenge is that at the output side, will you be able to reconstruct these samples? Just try to understand, have a kind of a physical scenario wherein, let's suppose this is your information signal at the transmitter side. In between there is some communication channel through which you are transmitting these samples, but the problem is you cannot accommodate all the 10 samples in this channel, so you do time scaling. Instead of 10, you scale it down to 5 samples. Now 5 samples can be accommodated in this channel, that is actually you will be time scaling, and this signal will be through the channel. Then on the receiver side, what you are receiving is this, assuming that there is no noise in the channel. Fine. The challenge is whether you will be able to reconstruct your entire waveform from this received waveform. This is the challenge. Fine. And hopefully we will see in the coming, whether in this course, yeah, in the courses that you will be dealing in higher semesters, that we have certain laws wherein this is possible, that even after you scale down, you lose some samples, you then, because when you lose samples, you kind of conserve your bandwidth job with this communicating medium. You can use it efficiently because instead of 10, you're only transferring 5 samples. Fine, but at the receiver side, you should be able to get back your original samples. That is the challenge. Fine. Similarly, if we consider shifting, you're not losing anything. Your original signal has 5 samples. Your shifted signal also has 5 samples. But what you are doing is you are shifting the waveform. Fine. Again, at this point of time, you may not be able to physically interpret it in a better way, but just at the back of your mind, have this thing that physically something is happening. You're not losing any information. Please mind it, you're not losing any information in shifting because your waveform is intact. Only thing is it is being shifted. It is being shifted along the time axis by some amount, either to right or to left. We'll stop here. Further discussions will follow in next videos.